All right, so we're at our first theorem of chapter 3, which is full of theorems, very important theorems. This one doesn't have a name; it's just called the theorem. But here's what it says: a polynomial function of degree n can have at most n zeros and at most n minus one relative extrema. What's another name for relative extrema? Yeah, local max or mins. Okay, that means at most, at most. So a fifth degree polynomial can have at most five x-intercepts. That's another name for zeros or roots, same thing, right? So we're kind of used to that with a quadratic, right? If we just look at degree 2, we have a polynomial. It looks like this. This has zero roots. I call them roots. That's how I learned them growing up. They're called zeros or x-intercepts. There's zero roots. It could be that it has this boing and bounces. This would be one root. It would bounce. Or it could be, bless you, that it crosses on the way down and crosses again on the way up. That would be two roots. Okay? So that's the most it can have. There's no way a parabola, which is degree 2, can have 3 x-intercepts. There's no way. Okay? 2 at the most. But it can have any combination less than 2. Now, in terms of relative or local max or mins, a polynomial of degree 2 can have at most one local extrema. And a polynomial of degree 2 has exactly one relative extrema. Can a quadratic have 0 relative extrema? According to this, it can have at most n minus 1, so at most 1. So you're saying I can draw a quadratic that has no local max or mins. Let's see. If I come in the top, a polynomial has to have the same end behavior, right? So how am I going to go out the top if I'm not allowed to have a local minimum? I have to turn around somewhere, don't I? Yeah, if I'm really degree 2, I got to go back out the top. And guess what? Right there, wherever I turn around, you're going to have a local max or min. So a quadratic can have at most one local max or min, and it has exactly one max or min. Oh, then that's not a function of x. We're talking about ones that pass the vertical line test. Yeah, good question. We're talking about polynomial functions of x that pass the vertical line test. All right, let's just look at some possibilities here. Draw several possibilities for the shape of a polynomial of odd degree. Use the fifth degree to polynomial as an example. Okay, analyze for zeros and local extrema. So we're going to look at degree 5. The parent function for degree 5 is f of x equals x to the fifth. And we know that that one comes in like this, and like x cubed, it goes to the origin right there, and then it comes out like that. The only difference is between -1 and 1, this graph is flatter than x cubed, and outside of -1 and 1, it's steeper. Okay? How many zeros does this one have? One root. It has one root. How many local extrema? 0. I'm just going to call it 0 LE, local extrema. One root and 0 local extrema. Does that still abide by the theorem? The theorem says it has at most 5 x-intercepts. This one has 1. And it has at most 4 local max or mins, and this one has 0. So that's true. Okay, now, here's what else we could do. Bless you. If you really expand it out, and you draw it to its maximum capability with 5 x-intercepts, here's what it's going to look like. It's going to cross 1, 2 times, 3 times, 4 times, 5 times. It'll look like that. Okay? We don't know what this equation is, but it's going to look something like this. It's going to be ax to the fifth plus bx to the fourth plus cx cubed plus dx squared plus ex plus f. Okay? Whenever you add multiple terms behind the leading term, that's when you start introducing wiggles. So if you want to make that note right here, more terms equals more wiggling. Okay? How many x-intercepts does this one have? 1, 2, 3, 4, 5. This one has 5 roots or 5 zeros. And how many local extrema? 4. It has 4 relative or local extrema. Now, according to the theorem, is this the maximum number of roots and the maximum number of local extrema this one can show? It is, right? There's no way you're going to have 6 roots and be a fifth degree polynomial. There's no way you're going to have 5 or 6 local extrema and be fifth degree polynomial. Or you can have fewer. Now let's look at one that has fewer. Okay. What if it comes in the bottom? There's one x-intercept, two x-intercepts, three x-intercepts, but then it does something like this. It turns like it's going to turn around and go back down, but instead it goes psych and it goes back up. This, believe it or not, is also a fifth degree polynomial. How many x-intercepts do you see? 3 roots. And how many local extrema? 2 local extrema, right? 2 local extrema.
Is that the one that starts to go up and it goes like flat? What if it starts going down? Would that be?
That would be another relative extrema. Yeah. Yeah. So it could do this. It could cross once, twice, 3 times, and it can actually turn around but not go back down to the x-axis. Yeah. So let's look at that one. How many roots does this one have? 3 roots. And how many local extrema does this one have now? 1, 2, 3. It's back to what? 4. Yeah, it's back to 4 local extrema. What if I took that graph, and let's start over here now. What if I took that same graph, but I went like this? I went 1, 2, 3, and then when it came down, oops, I held on to it too long. What if it did that? How many x-intercepts would it have now? 3. Okay. That's not worth drawing. Let's do this. What if it does this? 1, 2, 3, and then it comes down and bounces. There you go. That's what I wanted to do. What if it bounces for that next one? How many roots does it have now? 1, 2, 3, 4 roots. 4 roots, and it's back to 4 local extrema. Yeah. So let's see. I've drawn it with 5 roots. I've drawn it with 4 roots. I've drawn it with 3 roots. You think we could draw it with 2 roots? Let's see if we can draw one with 2 roots. 2 roots would be something like this. It would come in and it would bounce once, twice, and do something like that. 1 root, 2 roots. So there's 2 roots. How many local extrema would it have?
4.
Still 4. Can I draw it with 1 root? Well, we've already drawn it with 1 root, right? The parent function had 1 root. Can we draw this with 0 roots? Why, Wyatt? What do we know? I think you're on it. What do we know about the end behavior? Same or opposite? Opposite, okay. So we can't draw with 0 roots because the end behavior is opposite.
But if it was even, it could have 0.
Right, yeah. So an odd degree polynomial can have up to n x-intercepts and any combination down to 1, but it can't have 0 because of the nature of the way it comes in and goes out. It has to cross the x-axis at least once. Okay. Now let's look at the local extrema. We drew it with 4 local extrema several times. We drew it with 4 local extrema several times. We drew it with 0 local extrema, and we drew it with 2 local extrema. 0, 2, 4. 4 would be the maximum, right? That's n minus 1. Do you think we could draw it with 3 local extrema? Let's try it. Let's try to draw it with 3 local extrema. We'll come over here, draw a little x and y axis. 3 local extrema means I'm only allowed to turn around 3 times. So let's say I come in the bottom, I turn around once, I turn around twice, I turn around 3 times. Is it going to work? No, okay. We can't have basically an odd number of local extrema because it ruins the end behavior. Okay, so what does that mean? We can have a max up to n minus 1 in pairs. you have to have your turning points in pairs. If you turn around once, you got to turn around again to make sure you're on track for the right end behavior. Does that make sense? So a fifth degree polynomial can have what combination of roots? Of roots, x-intercepts. Can it have 5? You can have 4, 3, 2, 1, 0? No. So it can have 1, 2, 3, 4, 5, but not 0. Local extrema for a fifth degree polynomial. Can it have 4? Yes. Can it have 2? Yes. Can it have 0? What about our parent function? Yeah, it can't have 0. We have to count by 2s. Can it have 1 turning point? Can it have 3 turning points? No, it can't have an odd number of turning points. So that's why we say it has at most n minus 1 relative extrema, and then you could say in pairs. If you want to add that to the theorem, the relative extrema have to occur in pairs. All right, let's do the same thing for an even degree polynomial. We'll use a fourth degree Taylor polynomial or a fourth degree polynomial for our analysis. So all of these will be degree 4. We'll start with the parent function. The parent function is the one that looks like a parabola. It just opens wider. How many roots do you see? 1 root. How many local extrema? 1 local extrema, right? One local min. All right. Can we draw this one with 2 roots? Yeah, let's see if we can draw one with 2 roots. With 2 roots, it should be very, very similar, right? In fact, watch. All I have to do is copy this one, paste it here, and then grab my parabola and move it down, right? If I move it down, now I have 1, 2 roots, and how many local extrema? 1 local extrema. Okay, let's see if I can draw it with 3 roots. Can I draw it with 3 roots? Well, you're not quite sure yet. Let's go ahead and draw it with the maximum number to do that first. What's the maximum number of roots according to the theorem a fourth degree polynomial can have? No? It can have n roots, so it can have maximum 4 roots. Yeah, 4 roots or zeros. Okay, here's what it would look like. Let's have it come in the bottom this time. It's going to come in cross, 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 and cross. It'll look like the M yesterday or the W if it opens up. Okay, you got 4 roots and how many local extrema? 3 local extrema. Is that the maximum number of roots and the maximum number of local extrema by the theorems? If it's degree 4, yeah, I can have 4 roots and 3 relative extrema. Okay, good. Let's see. We have 1 root, 2 roots. Let's see if we can draw with 3 roots. Let's see if we can draw with 3 roots. With 3 roots, it should be pretty easy. Just come in and cross, bounce on one of them, and then cross like that. And now I have 1, 2, I have 3 roots, and I still have 3 relative extrema. Very good, very good. Can we draw with 0 roots? Actually, this one we can, right? All I got to do is come in the top. I can turn around and watch. If I do this, that's what a fourth degree polynomial can look like as well. It can look something like that. I have 0 roots, and how many local extrema do I have? I look like I'm going to turn around here, but I don't. I continue back up. So it's still just 1 local extrema. So I've seen the combinations 0, 1, 2, 3, or 4 roots, and then the combinations on the local extrema up to n minus 1, but they have to occur in pairs, right? So can I draw an even degree polynomial like a 4 with an even number of local extrema? No, it ruins the end behavior. So once again, we could say we can have any combo of roots up to n, including 0. An even degree function does not have to touch or cross the x-axis. But again, we can have maximum of odd n minus 1 turning points in pairs. You have to have an odd number of turning points. So an even degree function has to have an odd number of turning points, and an odd degree function has to have an even number of turning points. Would you agree? Okay. All right, so if you notice what I did on a couple of these, like up here on the fifth degree polynomial, I had right here, this right here, I call that a wiggle. If you put a value right there, this is a wiggle. It's really what's called an inflection point. And I think we've seen that term before. It's where the curvature changes. Okay? It approaches like it's going to turn around, but then it goes psych and it continues back up. That wiggle accounts for multiple roots that never happened. Okay? Same thing down here. I have another wiggle or another inflection point right there. And it accounts for some values that never occurred. Because here's what could have happened. I could have actually come up there. I could have turned around, and then I could have come back up. So that wiggle, which had 0 critical values, or I'm sorry, it had 0 local extrema, really could have had 2 local extrema, right? It could have. And if I actually wanted to turn around enough, I could have crossed and then come back up. So it accounted also for 2 x-intercepts. So the fact that it has a little wiggle, it really takes up what could have been more local extrema and more roots as well. So we get something what's called multiplicities, okay? Multiplicities. Let me show you what multiplicities are. Multiplicities are basically how often a root is accounting for. Not what it actually is doing, but what it accounts for, all right? So let's say you have a polynomial f of x in factored form, and it looks like this. Capital A, that's your vertical dilation factor from your standard transformation form. If A is negative, it opens down, and the end behavior is negative infinity. If A is positive, it opens up, and the end behavior is positive infinity. If you have it factored as x minus a times x minus b squared times x minus c cubed, notice the exponents on those factors. You have 3 x-intercepts here. You have x equals a. These are your roots. You have x equals a, x equals b, and x equals c. So if you plotted those, here's x equals a down here. You put a dot at x equals a. You put a dot at x equals b. You put a dot at x equals c. Here's what they look like graphically based upon how many factors they take up in the problem. If it is to the first degree, we call that a single root. It's a single root, okay, because it's a single factor. What does a single root look like? We call that a multiplicity 1, or M1, multiplicity 1. That means it occurs once. What does it look like graphically? Nothing. It just crosses. It shoots straight across. It's like a line that goes straight across the x-axis. It doesn't do anything special. If you have a double factor, or a factor squared, we call that a double root, which we say it has a multiplicity of 2, M2. It's a double root, multiplicity 2. That means it occurs twice. Guess what those look like graphically? They bounce, just like what your graph of x squared does. That's your parent function, x squared. 0 is a double root, and it bounces right there on the x-axis. So single roots cross, the exponent is 1. Double roots, the exponent is 2. Those are bounces. And the last one that y'all are responsible for is if it's a 3. We call this a triple root, and it has multiplicity 3. And what do those look like? Those are your wiggles. Okay, if you want to call them inflection points or wiggles, Ms. Skurlock said her class called them wobbles, but they actually wiggle. They change curvature there. It approaches like it's going to bounce, and then it goes psych, and then it continues down the other direction. Okay? So those are the 3 that you're responsible for. Crosses, bounces, and wiggles. M1, M2, M3. Now, it's important to realize that the multiplicities themselves, M1 corresponds to the exponent on the factor that generates that root. The multiplicity of 2 corresponds to the 2 exponent on the factor. Multiplicity of 3 corresponds to the exponent on the factor that generates that root. Okay? Does that make sense? All right, so we're going to tie those 3 together. Across, a bounce, and a wiggle. Across, a bounce, and a wiggle. Across, a bounce, and a wiggle. Now, let's see why it's called a double root. Real quickly here. This graph did not have to bounce on the x-axis. It could have crossed and then come back up, right? And had it crossed and come back up instead of bounce, how many x-intercepts would it have shown? It would have shown 1 there and 1 there. 1 on the way down and 1 on the way up. So it accounts for 2 x-intercepts. That's why we call it an M2. It bounced, but it took up the possibility for 2. This one is a wiggle. It could have crossed and then come up and then come back down. Like if you imagine taking that and twisting it counterclockwise around x equals c, you'll see that it could have looked like that. And it accounted for 1, 2, 3 x-intercepts and 2 local extrema. So a wiggle, by naturing of just acting like it's going to turn around and not, takes up the possibility of 3 x-intercepts. And that's why it's a triple root. Okay, here's another theorem. This is probably the most important theorem. We use this a lot. We already use this. We're just going to state it differently. X minus a is a factor of a polynomial function if and only if x equals a is a root or a 0, either way, a root or a 0, or an x-intercept, remember, of that polynomial function. Now, it's an if and only if theorem, so it works the other way around. If x equals a is a root, then x minus a is a factor. So if you know a root, you know a factor. If you know a factor, you know a root. Here's an example that we've already been using. Let's say I asked you to solve this right here. X squared minus 4 equals 0. Let's say I asked you to solve that. Bless you. And you solved it by factoring. This is x minus 2, x plus 2. Remember I said we're at the point now in honors where we don't have to physically set each of those factors equal to 0. You should be able just to look at the respective factor and tell me what the root is, right? So if x minus 2 is the factor, what's the solution to this root? Positive 2. If x plus 2 is the factor, what's the solution of the root that corresponds to it? Negative 2. That's using the factor theorem. It basically says if you know a factor, you know the root. If you know the factor, you know the root. It's just the value that when you plug in there makes it 0. Well, it works the other way around as well. If I told you x equals 2 is the root, guess what a factor is? X minus 2. And if I told you x equals negative 2 is the root, guess what the corresponding factor is? X plus 2, x minus negative 2. That's the factor theorem. It works both ways. If x minus a is a factor, then x equals a is a root. And if x equals a is a root, x minus a is a factor. So if you know a factor, you know a root, and if you know a root, you know a factor, right? And if you know a factor, you know a root, and if you know a root, you know a factor. Very good. Additionally, if we know what the exponents are on those factors in the function, we know what it does graphically at those x values, don't we? At the roots. It either crosses M1, it bounces M2, or it wiggles M3. You ready to try one out? Let's try one out. Example 7. Sketch the graph of the following function. Okay. F of x equals negative 5x times x minus 3 squared times x plus 2 cubed times x plus 5 squared times x minus 6. It says to state the leading coefficient and the degree of the polynomial. Let's do that first. Okay. First of all, let's talk about the degree of the polynomial. This is in factored form, right? But if you were to expand it out, you would have an x to the first, an x to the second, an x to the third, an x to the second, and then you'd have another x to the first. Guess what the sum of all exponents gives you? It equals the degree. The sum of all the, I should say, of all the variable. The sum of all the variable exponents equals the degree. So what does that give us? That gives us 1 plus 2 plus 3 plus 2 plus 1, which ends up being what? I think it's 9, isn't it? So that gives, it's a 9th degree polynomial. It's a 9th degree polynomial. What is the leading coefficient then? What's a sub 9? If you would expand all this out, what number would be in front of the x to the 9th term? Yeah, it's the number that's actually out in front. It's right there. It's negative 5. So what does that tell us about the right end behavior? What's the limit as x goes to infinity of f of x? No. Remember we said this yesterday. The leading term sign gives you the right end behavior. So we know it exits the bottom, right? It's bottom out. Ah, very good. Now we know because it's an odd degree polynomial, what's the left end behavior? Positive infinity. So it's top in, bottom out. It's going to look something like this. It's going to come in, and it's going to have as many as like 8 turning points, and it's going to go out the bottom. Something like that, right? Something crazy like that. Well, we could actually sketch it. Let's go ahead and sketch it. Give yourself a y-axis, give yourself an x-axis. Let's go ahead and list the roots. What are the zeros, or the roots? I'll call them roots. Let's just list them from left to right. It's x equals What's the first zero that corresponds to the factor x to the first? 0. Now let's add the multiplicity there. It's a multiplicity what? 1, right? So we know that that's going to do what graphically? Bounce, cross, or wiggle? It's going to cross. Okay, I'm going to put 0 down there on my graph. All right, comma, what's the next root? If x minus 3 is the factor, what's the root? 3. So I'm going to put x equals 3, and what's the multiplicity there? 2. It's the exponent, so that's going to bounce, cross, or wiggle? It's going to bounce. Okay, so I'm going to come out here, 1, 2, 3, and I'm going to put that x-intercept. Okay, got it. The next x-intercept, if x plus 2 is the factor, what's the root? Negative 2, and it's a multiplicity 3 because that's the exponent, so that's going to wiggle there. So I'll come in here and put a negative 2 and put another value. And then the next root, x plus 5 is the factor, so negative 5 is the root, and it's multiplicity 2, so that's another bounce. So let's go ahead and kind of keep going, put the root negative 2, negative 3, negative 4, there's negative 5. And then finally, the last root is 6, and it's M1, so it's a cross, so 3, 4, 5, 6, and there we go. Okay, now that I have all my roots and I know what I'm supposed to do at each of them, I'm going to come in on the left-hand side. Now the question is, do I come in from the top or do I come in from the bottom? We've already talked about that. We come in from the top. Why do we come in from the top? Let's review why we come in from the top. Because the leading coefficient is negative, my right end behavior is negative infinity. So it's bottom out. Now because it's an odd degree, the left end behavior is the opposite, which is positive infinity, so it comes in from the top. Okay? So come in from the top and start approaching negative 5. I'll just do it with the highlighter. What do I do at negative 5? I need to know if I'm going to bounce, cross, or wiggle so I can make my approach. I bounce at negative 5. Okay, so as I come in, I'm just going to go boing like that. I'm going to bounce at negative 5. Okay, now I need to know what I'm going to do at negative 2. What am I going to do at negative 2? I'm going to wiggle. So I need to turn around quickly and approach like I'm going to make a smooth landing. Approach like you're going to bounce, okay? And then what do? Instead of bouncing, you go psych and you turn it back down. Now I need to know what I'm supposed to do at 0. 0 is a what? It's a cross. So I need to turn around and just go right through the origin. Turn around and go right through the origin. Okay? Now what am I supposed to do at 3? A bounce. So I just turn around somewhere where it's convenient and I approach like I'm going to bounce. And this time, instead of going down like a wiggle, I actually bounce and go up. And then at 6, what am I supposed to do? Cross, so I can turn around somewhere where it's convenient, and then head back down through 6 and just cross right through it. And there's the graph. I drew it with a highlighter on accident, but it works. When you draw your functions, I need to clearly be able to tell the difference between a cross and a wiggle. If I can't tell the difference between your crosses and your wiggles, you're going to lose points. So how can we make sure we're approaching a wiggle correctly? You approach it as if you're going to bounce, okay? You approach it as if you're going to bounce, okay? Think about it as you're going to bounce, but instead you psych it out and you turn back the other way, okay? And a cross is there's just no wiggle change, right? There's no curvature change. You just go straight through. You got it? Those are the two hardest to kind of distinguish between. You approach like you're going to bounce, and you make sure you change the curvature there. It goes from part of a smile in this case to part of a frown. It goes from part of a smile to part of a frown. Okay, kind of like an S. All right? Now, there's the graph. We sketched it. That's all we have to do. Can we talk about the domain? What's the domain of F? All real numbers. What's the range of F? Can we do that? All real numbers. How many x-intercepts? How many roots do we have? 1, 2, 3, 4, 5 roots, right? But if you add up all their multiplicities, what does it add up to? Yeah. If the multiplicities are the exponents, and the exponents add up to the degree, guess what the sum of the multiplicities is also? The degree. The sum of the multiplicities equals the degree. So every root is accounted for up to the degree. Every root is accounted for up to the degree. Some of them count once, some of them count twice, some of them count 3 times. How many local extrema do we have? We have 1, 2, 3, 4, 5, 6. Is that a legal number? Yeah. For an odd degree like 9, it has to have an even number of turning points. An even number. Yeah.
On the equation that says -5x, what if it was just -5? Would you?
Then x equals 0 would not be a root.
So would you distribute that -5 into the first term?
No, but when you expand everything out behind it, the -5 would still be in the front. -5 would still be your leading term. Your leading term, whether it's expanded or factored, is always in the front. Okay? That's what this A is right here. This A in this equation up here, this A is your leading coefficient. It's just in factored form. Okay? That's your leading coefficient. Good question. Good distinction. All right. Y'all think y'all could do one like that?
Yeah.
Okay. Now that one was easy because it was given to you in factored form, right? What if I'm expecting you, like on example 8, to sketch something and it's not in factored form? You think having factored form was helpful? Yeah, so guess what the first thing we're going to do? We're going to find the zeros by factoring it. So let's go ahead and do that. We'll set it equal to 0. I'll get -2x to the 4th minus x cubed plus 3x squared. And I need to show that I'm setting it equal to 0. When you're finding the roots, when you're finding the zeros, when you're finding the x-intercepts, you show me that you're setting it equal to 0. Now that it's equal to 0, we'll factor it. What's the first rule of factoring? Panic? Well, not the least common factor, the greatest common factor. And if you ever have a negative in the front, you also want to factor out the negative. So I'm going to factor out the negative, and what else do they have in common? X squared, that's it, right? And that leaves me a positive x squared, and it leaves me a plus x, and it leaves me a -3. Oh, it has a 2 there as well. Don't forget the 2. It's a 2x squared plus x minus 3 equals 0. All right, now, I focus on this. Does 2x squared plus x minus 3 factor anymore? I hope so, right? I sure hope it does. So I got -x squared, and I'm going to turn this into a double bubble, and I'm going to factor it by guessing and checking. Remember we've done that this year a little bit? 2 is not a 1, so it's not the easy type where the leading coefficient is 1, but 2 is prime, so it's got to be a 2x and a 1x. Now it's either a 1-3 combo or a 3-1 combo. That's it. It has to be one or the other. We're doing this right now in Algebra 2. If I do the 3-1 combo, my inside is 3x, and my outside is 2x. What's 3x minus 2x? 1x. Is that what we want? Yeah, so I know it's got to be the 3-1 combo. Okay, so let's go ahead and just put that in there for real. It's going to be the 3-1 combo. And then which one is going to be positive, which one's negative? If my middle term is positive, the 1's going to be negative and the 3 is going to be positive. So now you can guess and check or FOIL it out quickly in your head. You get 2x squared on the first. You get -3 on the last. Your outer is -2. Your inner is +3. That gives you a 1x, and we got it. Now, don't set each of these equal to 0. We're past that, aren't we? We are past setting each of those equal to 0. We're just going to use the factor theorem to generate the roots of the zeros. Okay, they're going to be x equals what? What's the first one from left to right? 0, and its multiplicity what? 2. So we're going to list the multiplicities behind them. All right, what's the next root? If you set 2x plus 3 equal to 0 in your head, you get -3 halves. -3 halves, and that's multiplicity what? Multiplicity 1. Okay, and what's the next root? +1, and its multiplicity what? 1. So what is the sum of those multiplicities? What's 2 plus 1 plus 1? 4. Is that the degree of our polynomial? Yes. Okay. So now that we have that, now we can sketch the graph. Give yourself an x and y axis. We got 0. We've got 1. And then we've got -3 halves, which is right here. Let's also talk about the end behavior. What would be the limit as x goes to infinity of p of x based upon the leading term? The leading term is -2, right? So the negative tells us the right end behavior is what? Negative infinity. Now, because it's an even degree, what do we know about the limit as x going to negative infinity? It's the same. It's negative infinity, right? Now, here's kind of a nice little thing. If it's an even degree polynomial, because they come in and go out the same way, you can still kind of stick with your intuitive opens down remark to yourself. It opens down. You can't really do that with odd degrees because they don't really open anywhere. They come in one side and go out the other. But an even degree always has the same end behavior, so you can always verify and say, oh, it opens down. The two end behaviors are negative infinity. So as I come in from the bottom here, what do I need to do at negative 3/2? So I cross, wiggle, or bounce. I cross, and I need to know what I'm doing already at 0. What do I do at 0? I bounce. So I approach it, and I go boing, and I bounce. I bounce right there. And then what am I going to do at 1? I cross. So I need to turn around comfortably. It's going to look a little squirrely, but I need to turn around comfortably. I don't want to go too high. If you go too high off the x-axis, it's not going to look good. Now, if you were to graph this on your calculator, it would be much, much different. The vertical piece would be very, very steep. We're trying to draw it so that we can make sense just by glancing. This is an M1, this is an M2, and this is another M1. And there's what your graph looks like. It's kind of like McDonald's again. Yeah. All right, what's the domain of this function? All real numbers. Can we find the range? Not without calculus or a calculator. It's bounded above for sure by one of those two local max. How many local extrema do we have? 3. We have 3 local extrema. 2 maxes, right? 2 local maximums and a local min. We actually know the local min, don't we? Yeah, we can actually say local min of y equals 0 at x equals 0. Yeah, but the 2 local maxes, we don't know. If you know calculus, you could find them, but that's next year, people, if you're a junior. If you're a senior, you might take it next year in, at the university, college. Okay. So far, so good? So good so far. We got 10 more minutes. That's time for example 9. Yeah, example 9. It says to let h of m, or equal that. Find the roots by factor by grouping, then sketch it. Okay, so the same thing. We want to find the roots. So I'm going to come down here. I'll use monochrome gray. I'll use gray. I don't use gray that often. M cubed minus 2m squared minus 4m plus 8. To find the roots or the zeros of the x-intercepts, is it important to show that we're setting it equal to 0? Yes, on a quiz that we might have tomorrow or something. On a quiz that we might have tomorrow or something, you would get a check for setting that equal to 0. Okay? Now, because there's 4 terms, it tells us to factor it by doing what? Grouping. So I'm going to group the first 2 together. I'm going to group the second 2 together, keeping the negative inside, and then you got to squeeze a plus sign back in between them. If you don't squeeze this plus sign back in between them, it's RONG wrong, because you've turned it into multiplication now. All right, now in the first 2, we look for a common factor. That's what we do. We look for GCFs in the 2 pairings. What's common in the first one? M squared, and that leaves us M minus 2. What's common in the second one? A 4, but if it's negative, we factor it out. So we factor out a negative 4, and we're left with M minus 2. Is it still equal to 0? Yeah. Now, the way factor by grouping works is you'll see that binomial factor reappear. So I can pull that M minus 2 out, and what am I left with in the first term? M squared, and what am I left with in the second term? Minus 4. Now, are we done factoring? No, I have now, appearing before my very eyes, is the difference of 2 perfect squares. So that continues to factor. The m minus 2 is still there, but now this is a conjugate. M minus 2 times m plus 2 equals 0. Is that completely factored? Yeah. Now, if you wanted to list the roots, you would say m equals 2 and m equals 2. Oh, wait. How many m minus 2 factors are there? There's 2. So this is really now m minus 2 squared times m plus 2. And there is the prime factorization. Now let's use the factor theorem. What's the first root if m minus 2 is the factor? 2. And what multiplicity is it? 2. So that's going to be a what? A bounce across or a wiggle? It's a bounce. What's the next root? If m plus 2 is the factor, negative 2 is the root, and what is the multiplicity? 1. So that's a what? Bounce, cross, or wiggle? Cross. Okay. So now all we got to do is sketch it. We'll come over here to negative 2, put a dot. Come over here to positive 2, put a dot. Now, in order to sketch it, we need to know something else. We need to know the end behavior. So Let's do that right here. The limit as x goes to infinity of h of m, I should say as m goes to infinity, not x, is positive. Yeah, why is it positive infinity, Peyton? The leading coefficient is positive. It's positive 1. So remember, that always gives you the right end behavior. Always the right end behavior. Now, to find the left end behavior, all I have to do is look to see, is it an even degree function or an odd degree function? It's an odd degree. So the odd degree has what? The same or the opposite? Opposite. Hey, they have the same sound, don't they? Odd, opposite. Odd, opposite. They both have the annoying ah sound. I wasn't feeling good when I started the lesson, but I'm starting to feel better now. You know why? Math is medicine. Keep that in mind. All right. So it comes in on the left side from where? The top or the bottom? It comes in from the bottom because the left end behavior is negative infinity. So it comes in from the bottom. And what's it going to do at negative 2? Negative 2 is a cross, right? So I just shoot straight across. Yeah. You got to keep them straight, right? That's why we labeled them over there. And then at 2, I'm going to bounce. So I approach as if I'm going to bounce. You got to really turn the curvature around on itself. So now it's part of a smile, part of a smile. And do I curve down or curve up from here? I curve up. It's a bounce. Yeah, so it's curved up on both sides. And there's the graph. There's the graph. What's the domain? All real numbers. That's easy. What's the range? All real numbers. Yeah. How many local extrema do we have? 2 local extrema. Yeah. We have a local max that we don't really know what it is. Do we know where the local min is? We do. We have a local minimum of y equals 0 at x equals what? 2. We don't know the local maximum because we don't know calculus and we don't have our calculator. All right?
So tomorrow on the Canadian quiz,
Yeah.
can we just list like 2 values?
Yeah, I might ask you to tell me how many it has, and then I might say, give me the location of any that you can actually pinpoint. So in this case, we can pinpoint the local min. All right. Example 10. This is going backwards. This is giving you the information, having you write the equation. I think I want to hold off on that. Okay? I want to understand it going forward before we understand it backwards. So I know there's like 4 minutes left. You can use that time to absorb what we talked about today, get ready for the next class, or get ready for tomorrow's possible quiz. On tomorrow's possible quiz, you might have to sketch something like this. Because it's a quiz, I don't want to mess you up on factoring, but if I give you something like this, that's in purely factored form, you should be able to sketch the graph. You should be able to have the right thing happening on the right x-intercepts based on their multiplicities. Okay? I probably won't quiz you on factoring tomorrow, because if you can't factor it, you can't answer the rest of it. On the test, you'll have to factor for sure. And on your homework, there's lots of factoring. Factoring is super important because that gets us to this stage right here where we can decipher it. But on the quiz tomorrow, I'll probably just give you it in factored form so we can do it quickly. I might give you 2 of them, though. I might give you one that's an odd degree and one that's an even degree. Okay? All right. Yes?